Okay, so I want to talk about how this idea of confidence interval and hypothesis testing is kind of related. Okay, we work with confidence intervals when we are examining a sample and we're trying to generalize what that sample means to the entire population. We're never really interested in what the mean or standard deviation of a sample is. We're only interested in it because it gives us a clue as to the mean and standard deviation of the entire population. Of course, we don't have the resources usually to measure the entire population, so that's why samples are so important to us. Okay, now there's certain dynamics that we started to see that go on with samples, and one of them is that if we know the mean and the standard deviation, sigma, of a population, if we know that about a population, then we can take any sample of size n, right? I'm going to start off with, say, a sample of size 100. Okay, and we know that if we take samples of that size over and over and over again until we get, many sample means of sample size 100 from that population, if we then draw a distribution of all the sample means that we would get, then we would see that the sample mean, right? The sample means the x bars, right, are going to be equal to mu. Sometimes we'll get a mean for a sample of 100 that's under mu. Sometimes we'll get one that's over mu. But most of them are going to be close to what mu is, what the population mean is. Now, we do know that since we're taking a sample of 100, the actual values of all those sample means are going to be much tighter, much less widely distributed than the actual population is. Okay, and there's a relationship here. The standard deviation, the standard error, or standard deviation of the sample means, which we call standard error, is equal to the standard deviation of population divided by the square root of the sample size. Okay, in this case, the standard error is 1/10 the size of the standard deviation of the population because we took a sample of 100. We could have taken a sample of 25. We could have taken a sample size of 25. We could have taken a sample size of 5, anything we wanted. Okay, so unfortunately, we rarely know the mean and the standard deviation of the population. So this really doesn't do us too much good because we don't really know that often. So in that case, we can't really use this effectively. So what we wind up using instead is if we take a sample of 100 people, and let's say we wind up and we say, let's say that we find X bar, the mean for that population of 100 people, is equal to, say, 50. And we find that the standard deviation is equal to 10. That's the standard deviation of the sample that we took, those 100 people. Well, we can use the standard deviation of that sample as a substitute for the standard deviation of the population, because it's going to, just like the mean approximates the mean of the population, the standard deviation of a large sample is going to approximate the standard deviation of the population. Is going to approximate sigma, right? Because it's a random sample. Okay, so now what that tells me then is that I can say to myself, well, the sample means, let's say that I can draw like an imaginary distribution here and say that I have X bars in the middle, right? And if I took samples over and over and over again, well, my standard error then is going to be equal to, instead of the standard deviation of the population, I'll use the standard deviation of the sample over the square root of n. Okay, so now my standard error is going to be equal to 10 divided by square root of 10 is square root of 100 is 10. So standard error is equal to 1. So now I can set up a range that I call a confidence interval. And I can say to myself, well, if indeed that this turns out to be the real population mean, I expect that there's a certain range in which I would expect all of the samples to fall. Okay, and that's going to be about 2 standard deviations below the mean. I would expect 95% of the samples to fall 2 standard deviations below the mean, or to 2 standard deviations above the mean. We know in real life we're really talking about 1.96 standard deviations below the mean and 1.96 standard deviations above the mean. So I can create something called a confidence interval. I'll abbreviate it CI, confidence interval. And that confidence interval is going to be a range in which I'm 95% certain that the true population mean is going to fall within. The bigger the sample size is, the smaller my standard error, because I'm dividing by a larger number, standard deviation by a larger number. So that will allow me to say that the bigger sample size is, the narrower that confidence interval is, the narrower that range is within which I can say I'm 95% certain. So how do I create that? I say X bar plus or minus 1.96 standard deviations, okay, or in other words, standard errors for the sample means. Okay, so my standard error in this case is equal to 1, so it's X bar plus or minus 1.96. Okay, in other words, roughly 48 and 52. That's my confidence interval. That's how I use my confidence interval. Now, if I had said to you, gee, Tony, I'm comparing this to another population. This is population A. I'm comparing this to another population. And I happen to know that the mean of that population B, the mean mu, I happen to know the mean mu for one reason or another. The mean mu for that population B is equal to 47. If that's the case, I'm 95% sure that the population mean for A is between 48 and 52. I can say with 95% certainty that the mean of population A is different than the mean for population B because it's 47. It's outside of that confidence interval. I'm pretty sure, 95% certain, that I don't have the same mean because it's outside the range that I'm 95% sure the true mean of this population A is. So I can look at it that way. I can use the confidence interval kind of to compare this to a value of a mean of a known population. Okay, well, there's a couple of limitations here. One of the obvious limitations is that I'm assuming that we know the mean of population B, right? Well, there's also the other thing. I'm kind of applying this a little incorrectly. It's more correct to apply this a bit differently, and that is to actually create something called a hypothesis test. So I'm going to create a hypothesis test for this situation that I just described before. Okay, and I'm going to say to myself, okay, I got two populations I want to compare, population A and population B. Okay, now I know that population B is equal to 47. Okay, now I don't know what population A is equal to. However, I take a sample of size 100 and I find that X bar for that sample is equal to 50. And I find the standard deviation of those 100 values is equal to 10. Well, now what I can do is I can say to myself, how many standard deviations apart are the means for these two populations? In one case, an estimated mean. In the other case, a known mean. Okay, and this is what we call a single sample t-test. Okay, and the reason why I call it a single sample t-test is because one population you already know what the mean is, mu is equal to 47, but the other population you're estimating what the mean is based on a sample. So there's one sample involved. Okay, so now the way I would do this, I'd say to myself, well, how many standard deviations or standard errors apart are these two values? Are they far enough apart for me to say that distance, that amount, that the number of standard errors apart that they are, would only occur by accident or less than 5% of the time? In other words, am I 95% sure that I can say that they're different? Well, the way that I do this is I set up a hypothesis test. I start off with a null hypothesis, H null. And that case is always going to involve an equality, right? We're going to start with the assumption that they're equal, that the mean of the mean of the population for A is equal to the mean of the population for B, okay, which in this case is equal to 47. So I could actually say this two ways. I could say that mu A is equal to mu B, or I could just say that mu A is equal to 47 because I know what mu B is already. Okay, I could write this either way. And my alternative hypothesis, which is what I really want to prove, is that mu A is not equal to mu B. Okay, in other words, not equal to 47. Okay, again, you could set this up either way there. Okay, so now I'm not starting with the assume. I started to tell you the results for my sample from population A. Step back for a moment and say to yourself, well, I set up this hypothesis before I knew these results. So I didn't know if mu A, the population A, the sample that I take, the mean is going to be bigger or smaller than 47 or population B. So I set up a two-sided hypothesis. In other words, all I'm postulating is that I'm starting with the assumption that mu A equals mu B, and then I'm looking for the alternative that mu A is not equal to mu B. In other words, could be bigger or could be smaller. I don't know which to start off with. Okay, so here's our result. So let's see how many standard deviations apart these are. Well, I'm going to say the number of standard errors. What do we call the number of standard errors? We call that either the z-score or the t-score. I'm going to discuss in a second which one we're going to use. Okay, the z-score or the t-score, the number of standard deviations can be described as z or t is equal to x bar 1 minus mu, or the value of the sample minus the mean that we're comparing it to, over the standard error. Okay, and what is that? That's 50 minus 47 over the standard error, which was, we said before, that the standard deviation is 10, sample size divided by square root of 100, which is 10, is equal to 1. So that's equal to 3. There are 3 standard errors apart, or a z-score of 3 z-scores apart, or 3 t-scores apart. Well, if I know the population standard deviation for A, if I know that, I can use the z-score because I know the relationship sigma over the square root of n is definitely going to be equal to a true standard error. If I'm dependent on using the standard deviation over the square root of n, well, now I'm introducing a bit of uncertainty because I could be off on that because it's being derived from a sample, not from the actual population itself. So in that case, we use t instead of z. We use z when we know it. We use t when we don't know it. We got a little bit of another escape, though, too. If the sample size is very large, say bigger than 50, right? Say 50 or bigger. If the sample size, for the moment, for our purposes, say 50. If the sample size is bigger than 50, well, if it's that big a sample size, we have a pretty good idea how variable these numbers are. So I'm going to say we have a good idea what sigma is. We have a good enough estimation of sigma that we can just use the z-score instead of the t-score. So I'm going to go ahead and solve this. The z-score is equal to 3. So now if I go to my z-table, whoops, got to move that off of there so I can use this. If I go to my z-table, okay, and I look for what's the probability of getting a z-score that's three standard deviations, z-score 3. Now remember, it's double-sided, so we're looking for the area of the frequency or the probability that we would get a value as big as a z-score of 3 or larger. In other words, the tail on the left and the tail on the right. Well, I'm going to say minus 3 because it's right here. So minus 3 is only about a 1.3% chance of us getting that big a z-score if these two are from the same population. However, I have to account for a plus 3 z-score of 3, so that's 1.3% on the top. So on the right side as well. So if I add those two together, the probability of my getting a z-score as big as minus 3 or plus 3 away from the mean is about 2.6%. That's my p-value, my probability of having that outcome by chance when the populations really have the same mean. So if I go back to my if I go back to my hypothesis, I could say, well, they're so different that this outcome, this big the difference, 47 versus 50, this would only happen 2.6% of the time. So I'm not by accident. So I'm 2.6, I am 97.4% certain that I can reject the null hypothesis and accept the alternative hypothesis. Maybe a better way to phrase that is to say, I'm 95%, being 95% certain is the same thing as saying that I can accept a type 1 error, an alpha error of 5% or 0.05. Okay, I'm willing to accept that level of error. Okay, now what is the level of error? I called it P, or it's SPSS calls it significant. Level of error that I have is equal to 0.026, 2.6%. So my anticipated level of error, likelihood of being wrong, if I say that these are different, not the same, the chances of my being wrong and this result being due to chance is only 2.6%, which is less than my acceptable level of error, which is 5%. So I reject my null hypothesis and accept my alternative hypothesis. Now let's see what would have happened if this had been a sample size of, instead of sample size of 100, if this were a sample size of 25. Okay, now, if this were a sample size of 25, what would happen now? What would happen now is, well, first of all, what did I say about the sample size? What did I say is a acceptable level of sample size for me to use the z-score instead of t? Anybody remember what that was? I change every once in a while, so it's good for me to have you guys tell me. Okay, I said 50. Sometimes I'll say 30. Okay, a lot of professors will say 30. I'm going to use 50 for our purposes. Okay, so greater than 50. Now this is less than 50, so I can no longer use the z-score. So now I have to say to myself, how far apart are these in terms of the number of standard errors? Well, t is equal to x bar a minus mu b over the standard error. Okay, this time though, the standard error, what is standard error equal to this time? It's equal to 10 over the square root of 25, which is 5. It's equal to 2. So we have 50 minus 47 divided by 2. So my t-score now is equal to, this 3 divided by 2 is equal to 1.5. Uh-oh, something happened here. My loss of accuracy because of my sample size reduction led me to get a lower value for the t-score. Not only that, but now I really don't have a table that I can go to, like the z-table, that tells me every possible outcome for a t-score. Like if a t-score were 1.5, a z-score 1.5 is a probability in each tail of about 6.9%, right? So I know already that's going to be, if I double that, that's going to be greater than 5%. So I failed to reject the null hypothesis. But not only that, the t-tables, that I would need a different t-table for every sample size if I wanted that. So instead of being able to pull out an exact probability of p-score, I can go to a t-table, which then tells me what value of t I need for different sample sizes to be able to reject the null hypothesis. Well, in this case, we have a sample size of 25, which same thing as saying 24 degrees of freedom. So if I go down here to 24, well, for a right tail probability of 2.5%, in other words, double that, 5% right and left tail, or in other words, confidence interval 95%, that's our alpha is equal to 5%. For that level of confidence, for an alpha error of less than 5%, I have to have a t-score for a sample size of 25 degrees of freedom 24. I have to t-score that's greater than 2.064. Now, had we been working with the z-table, then we know that 1.9, we needed a z-score bigger than 1.96 to have less than 2.5% in each tail. You know, if you're outside of that 1.96, if it's greater, you know the tails are less than 2.5% on each side, so less than 5% alpha, okay, or p-value less than 5% when you add them together. So this t-score is going to have to be bigger 2.06, bigger than 2.06 in order for me to reject the null hypothesis. And I got a t-score of 1.5. Can I reject the null hypothesis? No, can't reject it, right? So I say I fail to reject the null hypothesis. Can I say I accept the null hypothesis? Right? No, I can't say that. I can't say that because we haven't proved anything, right? We haven't proved that the null hypothesis is true. We've just failed to be able to reject it. Had we been able to reject it, we would have said we reject the null hypothesis, we accept the alternative hypothesis. We weren't able to do that, right? So we failed to reject the null hypothesis. Now, someone else may go back and say, hey, I'll bet you we got a good shot with, if looking at this data, I got a good shot. I'll bet you if we take a sample size of 100 or 200, maybe we'll have a pretty good shot of rejecting the null hypothesis. And in fact, we kind of see that already, that indeed they do have a good shot of rejecting the null hypothesis if they're working with a larger sample size. Okay, so that's how we're dealing with this idea. That's kind of an introduction to this thing. Now, in real life, you're rarely going to be in a situation where you have a situation where you know what the population mean is for either of these two populations that you're comparing. Now, by populations, I'm talking about two different groups. This could be Frenchmen and this could be Americans. This could be people that took a drug. This could be people that took a placebo. This could be males. This could be females. This could be tall people. This could be short people. So populations can mean a lot of different things. Okay, but in any case, it's very rare that we would ever know what a population mean is. And in fact, if we knew what the population mean of A and the population mean of B both are, there's no need to do this. We know whether the means of the populations are the same or different just by looking at them, right? So we only have to do this in this kind of situation. But we very rarely know the mean and the standard deviation for both populations. In fact, we very rarely know for either population. Okay, so when we wind up in that situation, what do we have? We have two populations. We have population A and we have population B. Okay, let's say I take a sample size of 50 people from population A, and I take a sample size of 50 people from population B. And I find that X bar for population A is equal to 50, and the standard deviation is equal to 10. Okay, and now I go over to X, do it for X, I'll just put a little A down here. Okay, now I do it for B, X bar for B is equal to 47. Okay, those 50 people that I sampled come out with a mean of 47, and the standard deviation for those 50 people comes out to be, let's say, 12. Okay, so now I want to compare these two. And I'm going to do exactly the same thing I did before. I'm going to say to myself, either Z or T, right? I won't worry about which one right now because actually it's pretty big sample size, right? We're over 50, we're at 50 or larger. So I got a shot at using Z here. We know that already, right? I got a shot at using Z here. So I could say Z is equal to the difference between these two means X bar A minus X bar B over the standard error. Okay, so now I can actually go ahead and calculate that. I could say X bar A is 50 minus 47. Uh-oh, now I got a problem here. So what do I do about the standard error? There are several things that you could do with the standard error. One thing that you can do with the standard error is that you can say to yourself, you know, they look very close together. In fact, when one is not double the other, we kind of make the assumption that we can pool the 50 people and 50 people, we can pool them and calculate kind of a weighted average of standard errors between the two of them, and we can assume equal standard deviations or equal variances for the two populations, And we can calculate our standard error based on the standard deviation pooled, right, over the square root of the sample size, right? But now we have to calculate that. The other assumption that we can make is that, let's say this has come out to 10 and this has come out to 22, more than twice what that one is, then we have unequal variances, right, or standard deviations. So now how do we deal with that? Well, then we do our calculation for standard error. We do it somewhat differently. Okay, so now you have formulas for calculating the t-score based on the z-score or the t-score, right? The means are easy, right? Standard error, you have ways of calculating the standard error based on whether or not you can pool them, they're equal variances, or whether or not you're making the assumption they have unequal variances. Now, the formulas for this are a little complicated, right? In some cases, they can get a little bit hairy, right? But SPSS, when you're doing it through SPSS, it actually calculates these for you. Okay, so let's say we wanted to go ahead and calculate this. First thing I would have to do is make our assumption. Well, first of all, I also need to know when we calculate this, I need to know what my degrees, if I'm going to use, well, with Z, not so much, but if we decide that we have to use the t-score, right, I need to know what my degrees of freedom are, right? Well, when we use equal variances and we're pooling the standard deviations, typically it's just equal to the degrees of freedom is equal to the sample sizes added together minus 2, minus 1, minus 1, 50 minus 1, and 50 minus 1 together is equal to 100 minus 2, or 98. Now, if we're not pooling the standard deviations, we got a bit of a problem, and it's a complicated calculation for degrees of freedom. So what a lot of people will do is they'll just say, take the smaller of the two sample sizes and subtract 1 and use that as the degrees of freedom, just as a quick way to avoid doing that very complicated calculation. Again, SPSS will do those calculations for you, so you don't have to worry about that. Okay, so I'm not going to get into that right now, because tonight I want to go over some other basics. Some people had some questions about the exercise 3 and assignment 4, which is mostly confidence intervals and so on and so forth. So I want to save that for perhaps maybe a little bit tomorrow night and for Thursday. Actually, tomorrow night I'll review just a little bit, because I want to introduce something else, that idea of chi-square and odds ratio. But on Wednesday and on the weekend, I'll go into this in more depth with specific questions. Okay, let's open the floor. Actually, tell you the truth, I have some questions a couple of people have sent me already. Okay, and one of them is, I'm going to take this one first. The mean SAT score for population first year students, I think this was from one of the exercises, is 620. Standard deviations of scores in this population is 95. And okay, so we got we know let me just talk about this for a second. The mean SAT score for the population of first year students, right? So that means that mu for all first year students is 620, right? I'm going to make that bold. Okay, I'm going to make it bold. Let's see. There we go. There's bold. Okay, mu is equal to 620, and the standard deviation of the entire population, sigma, is 95. Right, so we know that about the population. An investigator believes that the mean SAT of the first year psychology majors is significantly different than the mean score of the population. Okay, the mean of a sample of 36 randomly selected first year students is 648. Standard deviation. I'm going to backtrack and do it the way it's most likely you're going to wind up with this question actually in class. Okay, so I'm going to say to myself, okay, so we know what the population standard deviation is, and we know what the mean of the population is. Okay, so now let's take a look at what our sample from psych majors. What do we know about psych majors? We know that the mean X bar of the sample is equal to 648. We know that the sample size is 36, and we're going to assume that the standard deviation of the of this. We know the standard deviation of the population. So we're going to assume the standard error is equal to 95 divided by the square root of the sample size, which is the square root of 36. Okay? Makes sense? Are you guys comfortable with that? My mean for the sample is 648. My sample size is 36. So assuming that the standard deviation of the two populations are the same, okay, I'm going to say that the standard error for my repeated samples of size 36 from this population is going to be equal to 95 divided by the square root of 36. Okay, so let's take a look at what my confidence interval would be. My confidence interval is going to be equal to, okay, and I'll go down here and I'll come back. Confidence interval is going to be equal to x bar plus or minus 1.96. Actually, I should be using the t-score here, right? So what is a t-score for a sample of size 36? And so if I can't find it here, let's see, back here somewhere. Here we go. For a sample of size 36, okay, it's between these two, so it's going to be somewhere around 2.03. So I'm going to say that it's going to be plus or minus 2.03 times my standard error, which is going to be equal to 95 divided by 6. Square root of 36 is 6. 95 divided by 6. Okay, which is equal to 15.8. Okay, so now I'm going to say to myself, okay, so x bar, which is 648 minus 2 times 15.8. I'm going to round this. I'm going to say this is 30 minus 31, 32. I'm going to call this 32 is equal to 680. I'm sorry, I'm subtracting. That's 616, right? And if I go the other direction, 648 plus 32 is equal to 5670. So I'm 95% certain that the true mean for the population of psych majors is between 616 and 670. That's my 95% confidence interval. Now, is the mean for all Hunter students outside of that confidence interval? Can I be 95% certain that is it 680? Okay, 680. Actually, it's the other direction we're really concerned about anyway. Okay, can I be 95% certain that can I be 95% certain that that it is not 620? Okay, confidence interval is 616 to 680. We're 95% certain it's between those two for the psych majors. Can I say with 95% certainty that it's different than the whole population, which is 620? Well, no, I can't, can I? Because it could be 620. 620 is within our confidence interval. It's not outside the range that we're 95% certain on. Okay, so this is a simple way that we might apply the confidence interval. Okay, so now, had I done this as a hypothesis test, had I done exactly the same thing as hypothesis test, it's a small sample, so I would use t. I'd say t is equal to, right? What's t equal to? It's equal to x bar, right? Psych majors, minus mu, minus the mean, mu for all students, divided by the standard error. So how many standard errors apart are these two? What's the distance in t-scores? Well, it's going to be equal to 648 minus 620 Yeah, 620 over my standard error, which is equal to 15.8. So how many standard errors apart are these two? What's the t-value for the distance between these two? Okay, get my calculator out. So that's going to be 28 divided by 15.8. I hope I zeroed this. Okay, so it's going to be 1.77. Okay, so now the t-score is equal to 1.77. Well, how far apart do they have to be for me to reject my null hypothesis? My null hypothesis was, by the way, my null hypothesis was that the mean for all students is equal to the mean for psych students. And my H-alt was the mean for all students is not equal to the mean for psych students. Okay, so how far apart in t-values and t-scores do these two have to be in order to reject the null hypothesis? Anybody remember how far apart? What's the critical value of t for a sample size of 36? What was it? It's already on this page. What's the critical value? 2.03, right, because we looked it up before, right? For 35 degrees of freedom, sample size at 36, 35 degrees of freedom was about 2.03. So the number of standard errors apart, or the t-score that we get for the comparison of these two means is 1.77. Can I reject the null hypothesis? Opinions? Can I reject? No, I can't reject the null hypothesis, right? I fail to reject the null hypothesis. See, now we just came to the same conclusion using hypothesis testing in the t-score that we were assuming was true based on the confidence interval that we calculated and comparing that to the value for the mean for the population, right? This was outside of our confidence interval. So we said there's not enough proof to say that they're really different. We can't be 95% sure that they're really different. And we just repeated that here. We decided we say to ourselves, well, I have more than 5% chance of being wrong if I reject the null hypothesis. So I don't reject the null hypothesis. The t has to be higher than the critical value to be able to reject. Yes. Okay. The p value has to be less than 0.05. The probability of being wrong, in other words, the probability that z or t represents, the bigger the t value or the z value, the smaller the tail of the distribution of samples, right? So as the t value goes up, the p value or significance goes down. So in other words, the critical value tells you that if you have that t value, the probability of being wrong is exactly 5%. So if you exceed that t-value, the probability of being wrong, if you reject the null hypothesis, is less than 5%. So you can go ahead and reject it. So your t-value has to be bigger than your critical value of t. Another way of looking at it is your p-value, your probability of being wrong, if you use a z-table, probability of being wrong has to be less than 5%. Okay, they're both the same. Small p-value, big t-value are the same thing. Okay, does that make sense? Okay, well, let me go over one more question here, and then I'll ask you guys if you have some stuff over here, some other stuff. That's this thing. Yeah, that one was missing. Well, no wonder you couldn't do that one. I didn't give you sample size. Same. Okay. When you make these up on the fly, it's kind of hard to. Could you go over question 4 from exercise 3? Yes, let's go over question 4 from exercise 3. Okay, I have that over here somewhere. Let me move this out of the way. There's stuff on my the stuff on my screen you guys can't see, so I have to move it around. That's exercise. Okay, problem 4 and exercise 3. Problem 4. Okay, let's take a look at this. In a clinical test with 2,171 subjects, 12,114 showed improvement from treatment. Find the margin of error for a 95% confidence interval used to estimate the population proportion. Okay, so now here's an example where, and I'm glad this came up because this is the other thing that you can come across. And that is that we discussed that you can have a situation where, this population mean, a population mean, and you're comparing it to a sample. You can have a situation where you have two samples and you're comparing the means of the two samples to one another, in which case you have to calculate the standard error based on assuming that they're equal variances or different variances between the two. We got formulas for that, and we'll be going over that tomorrow or Thursday, probably Thursday. Okay, and we're reviewing that again. It's in the, if you play the lab, the last lab we did, you'll see that we worked out some problems with each case of that. So now this is just an example where we're, instead of dealing with means of two groups, now we're dealing with proportions. Okay, and in this problem, the idea here is that in this case we took a sample of 2,100 subjects, and 1,200 of them showed an improvement from a treatment. So I'm going to copy that for starters. 1214, 2170, 1214, 1214 over 21, what was it? 2171. So the proportion of people in this study, now it's not everybody, it's people in a study, so that's PCAP, right? It's not everybody in the world that would be taking this drug in the future, right? It's a actual proportion in a study. Now, 1,214 out of 2,100 showed an improvement. Let's see what that proportion is equal to. Okay, let me clear this. 1214 divided by 2171 is equal to, it was 50, I'm going to call it 56%, is equal to 0.56. Did I do that right? Yes, 56% is equal to 56%. So now, what's the probability? Now that's this sample. Now, granted, this is a very large sample, so we have a pretty good idea that this is probably pretty close to what it would be like for an entire population if we gave this drug for everybody in a population that had this condition, right? So we have a lot of confidence in that, but we want to be able to quantify that confidence. So now when we know what a mean is from a sample, right? And we want to know what the population, how that relates to the population mean, right? We use a confidence interval. We're going to do the same thing here. So when we work with a mean, we need to know what X bar is, right? But then we also need to know what the standard error is for repeated samples of that size. Okay. Well, we need to do the same thing when we're dealing with a proportion, except that the point estimate in this case was a mean. The point estimate in this case is a proportion. So in order to calculate a confidence interval for what the true population proportion is, we have to figure out what to use as a standard error. So how would I do this? I'd say my confidence interval is my 95% confidence interval is equal to PCAP plus or minus 1.96, it's a very large sample, times the standard error. Well, how am I going to calculate my standard error? Well, for a proportion, we calculate our standard error by the square root of P times 1 minus P over the sample size. Okay, so now, if I look at this, I say to myself, what this really is, this approximation this is really a binomial distribution because it's yes and no. It's only two values here when you have a proportion. So this is basically a approximation of looking at the binomial distribution as being very similar to a normal distribution. And this is what's going to be our standard error. So what's this going to be equal to? The standard error is going to be equal to the square root of P, which is 0.56, times 0.44, 1 minus p, over the sample size, which was 2177. So if I work that out, that's going to be equal to, well, clear. If I work that out, that's going to be equal to, let's see, 0.56 times 0.44. That's equal to that, divided by 2177 is equal to this, and I'm going to take the square root of this whole thing. Here we go, square root. So my standard error is equal to about 0.011. Okay, so I'm going to call it 0.011. Okay, so my confidence interval is going to be equal to p cap plus or minus 1.96 times 0.011. Okay, so p cap is 0.56 plus or minus 1.96 times 0.011. Let's go ahead and calculate that out. Okay, 1.96 times 0.011, and that's equal to 0.02. I'm going to call it just 0.02, just for our purposes, is equal to plus or minus 0.02. So my 95% confidence interval for the true proportion P, not P cap, true proportion P is between 54%, 0.54, and 0.58. So I'm 95% sure that the true population proportion is equal to 54, between 54 and 58%. Okay. Now, would I say, would it be okay for me to say that I'm 95% sure that at least half of the people in the study were helped, half of the population will be helped by this drug? Would I be okay in saying that? Would that make sense? At least half of the population would be helped by using this drug. Well, half of the population would be 50%. 50% is outside of the confidence interval. So yeah, I could say with 95% certainty, more than 50% of the people that use this drug in this population would be helped by the drug. Okay, does that make sense to you guys? Did that clarify things just a little? I hope. Okay, so I'm gonna leave that here at this point. So tomorrow night we'll get an opportunity to just touch on this again and maybe just go over. I'm gonna maybe make up a example of each type of problem that you might run across when you have a known mean and a sample and a known mean, two samples with different means, with different standard deviations, two samples with similar standard deviations, proportions, and then we'll be looking at the this new idea of chi-square and odds ratios. Okay, so I think that's enough for now. And I know this is, this your first look at this stuff can be a little bit challenging, but I think with a little bit more attention to this stuff over the next few days, I think we can kind of nail this stuff down. Okay, so I'll see you guys tomorrow night, online or in person, one way or the other. And I'll talk about the exam and what's going to be on it, so you have an idea of what to expect. The ground rules basically will be the same in terms of what you can reference and so on and so forth. So you pretty much have an idea of what's going on there. So, but I'll give you an idea what the scope of it will be and what kind of problems you can expect to have. It's going to be more challenging than the first one because obviously the material is a bit more challenging, but I'm sure we're gonna get on top of it because I'm sure all of us are going to wind up figuring this stuff out as we go along. And I'll also talk about the next step on the project as well. Okay, so good night, guys. And again, I'll see you tomorrow night.